Hello friends, in this video we will see what is meant by homomorphism. You are all aware about the definition of a function. F is a relation from set A into the set B such that for every element of A there corresponds a element B belongs to capital V such that f of A equal to B. This B is a unique. Then this relation f is called as a function. Here in the book of Hustin, the notation of function instead of f of A we are going to write in a different manner. Instead of t of A, t is a function, we write it as t of A like this. So this is also a function. Now whenever we have two sets, suppose I have two sets, two vector spaces U and V. U is a vector space and V is a vector space over the same field F. Here we have taken F as a field. Then the mapping T is a mapping from say vector space V into the vector space V. U into the vector space A is said to be homomorphism if the first condition of homomorphism is that T of U1 plus U2 equal to T of U1 plus T of U2, and second condition of homomorphism is that T of alpha U1 equal to alpha times T of U1, alpha times T of U1. So if a mapping from vector space V U into V is satisfies these two conditions, then it is called as a homomorphism. Now if we draw a Venn diagram, suppose this is my U, this is my V, these are the two sets, and we have taken this U1 comma U2 belongs to U. Then look at this, U is a vector space, therefore U1 plus U2 is also a member of U. But whenever we take here T of U1 this one, T of U2, suppose this one T of U2, and we get here different image of this. This is a T of U1 plus U2. We have three elements. Now whenever this is equal to T of U1 equal to T of U1 plus T of U2, whenever T of U1 plus U2 equal to T of U1 plus T of U2 in V, these are all elements of V. Whenever this condition is satisfied, this is the first condition. Now as U1 belongs to U, we have alpha U1 is also belongs to U, and it is different from this one U1. Now alpha U1 it has a different image here. Suppose this is a alpha U1, T of alpha U1, it is member of V, and whenever this U1, T of U1 and T of alpha U1, these are two different elements, but if this relation between these two is satisfied, alpha times T of U1 equal to alpha T of U1 T of alpha U1. If this relation is satisfied, if these two conditions are satisfied, then it is called as a homomorphism. We combine these two conditions in single one, or we write it as a for alpha comma beta belongs to F and U comma V belongs to U. Whenever alpha U plus beta V T of alpha u plus beta v equal to alpha times T of u plus beta times T of v. If this condition is satisfied, it is called as a homomorphism. We write this here. I write like this: homomorphism condition alpha u plus beta v, T of alpha u plus beta v. If this single condition is satisfied, it is called as a homomorphism mapping alpha times T of u plus beta times T of v. This condition is important to prove the homomorphism mapping. Okay, we now we will see what is mean by what type examples of homomorphism. Consider a mapping. Suppose T is a mapping from vector space order tuple over the field R to order tuple over the field R. Now we defined. Now look at this. This set consists of order triplet. V3 is a it is of the type A comma B comma C, where A, B, C these are the members of R, and it is a order tuple. So it is of the type A comma B, where A comma B belongs to R. We have taken this mapping. Now we define this mapping like this. Suppose we have this element. This is a set of order tuple. This is set of order tuple, and for this element A, B, C, we define this mapping T of equal to A comma B. That means for T of A comma B comma C, I have image A comma B. This is my relation, this is my mapping, and we prove that this mapping is an homomorphism mapping. To prove this, we need two elements u and v from the set V3. Therefore we take u equal to, suppose, a1 comma b1 comma c1, and v equal to, suppose, a2 comma b2 comma c2. These are the two elements. Let us calculate alpha u plus beta v. Now what is alpha? Alpha times a1 comma a2 a1 comma b1 comma c1, and plus beta into v means a2 comma b2 comma c2. This is another element. Though let us multiply this. This is equal to alpha a1 comma alpha b1 comma alpha c1 plus beta a2 comma beta b2 comma beta c2. This is another element of, and addition is component wise. So this gives me alpha a1 plus beta a2 first element, alpha b1 plus beta b2 second element, and alpha c1 plus beta c2 third element. So again I will get an element of v3. Now let us take the image of this element. So we have T of alpha u plus beta v equal to T of alpha u plus beta v. That means T of alpha into a1 plus beta into a2 comma alpha into a2 alpha into b1, sorry, alpha into b1 plus beta into b2 comma alpha into c1 plus beta into c2, that is T of, but its image is order pair. Order pair means we get here alpha a1 plus beta a2 comma alpha b1 plus beta b2. This is a element. This is equal to, now again for this we write separately alpha a1 comma alpha b1 plus beta a2 comma beta b2, but this is equal to This is equal to what we get, alpha times a1 comma b1 plus beta times a2 comma b2, a2 comma b2. So I get this one, but this is equal to alpha into, this is nothing but t of u1 plus beta into, this is t of v, t of u plus t of beta into t of v. Now, so the given condition is satisfied, and hence this mapping is an homomorphism mapping. This is an example of homomorphism mapping. Now we will see again one more example of uh, homomorphism mapping. If suppose I have a mapping T, mapping T from R2 to R2, order tuple to order tuple, such that T of a comma b equal to a1, a plus 1, b plus 2. This is a definition of this mapping. Now look at this. If we take alpha equal to 0 and v equal to a comma b, this is a members of R2, then alpha v equal to 0 into a comma b equal to 0 comma 0. We get this one. Now let us see the second condition. What is second condition of homomorphism? Alpha t of alpha v equal to alpha times t of v. Then alpha v, left side of this condition, alpha v, t of alpha v equal to t of alpha v, we have calculated alpha v, that is t of 0 comma 0 equal to, by definition, what is definition? T of a comma b is a plus 1 comma b plus 2. This is equal to 0 plus 1 comma 0 plus 2. This is equal to 1 comma 2. Now see the right side, alpha times t of v. Alpha times t of v, this is equal to alpha, alpha is 0 times t of v. T of v is t of a comma b. T of a comma b 0 into a plus 1 comma b plus 2 equal to 0 comma 0. Now see these two values. These two values 1 comma 2 is not equal to 0 comma 0. This is not equal. That means here t of alpha v is not equal to alpha times t of v. Condition of homomorphism is not satisfied, and therefore the mapping defined by this relation, this is a mapping, this relation is not an homomorphism mapping. So this is an example of mapping which is not homomorphism mapping. Now we prove one lemma. Let me write the statement of the lemma. Lemma. if V is a vector space, V is a vector space over F, then first one, alpha into 0 equal to 0 for alpha belongs to F. Second is 0 into V equal to 0, alpha belongs to F. Third one is minus alpha into V equal to minus alpha V for alpha belongs to F and V belongs to V, capital V. V belongs to capital V. Fourth one is if V not equal to 0, then V not equal to 0, then alpha V equal to 0 implies that alpha equal to 0. And fifth one, alpha into V minus W equal to alpha V minus alpha W. So we prove this lemma for a vector space. Now let us prove first one, alpha into 0, alpha into 0 equal to alpha into 0 plus 0. We write this 0 as a 0 plus 0. Now apply the first condition of vector space. For first condition of vector space, what is first condition? Alpha times u plus v equal to alpha u plus beta v. This is first condition of vector space. Now we apply here first condition, we get alpha 0 plus alpha 0. Okay, again for this alpha 0 we write alpha 0 plus 0 equal to alpha 0 plus 0 is alpha 0 again, and therefore here we write here alpha 0 plus alpha 0. Now by right cancellation, left cancellation law, alpha 0 get cancelled and we get alpha 0 equal to 0. It is satisfied. Now 2, second part, 0 into V equal to, again we write it as a 0 plus 0 into V. Apply the second condition of vector space. What is second condition? Alpha beta into V equal to alpha V plus beta V. Apply this. So this gives me 0 into V plus 0 into V. Now for this alpha 0 again we write it as 0V plus 0V equal to here 0V plus 0V. Again by right cancellation law, we write this as here 0V. For this we write as a 0 plus 0 plus 0V equal to 0V plus 0V. This is not okay, I will cancel this. 0 plus 0V equal to 0V plus 0V. Now by right cancellation law, this 0V get cancelled and we get here 0V equal to 0. So second condition is satisfied. Now the third condition, we prove here third condition, 0 equal to 0V we have proved. Now 0 equal to, for this 0 we write here alpha minus alpha into V equal to alpha plus minus alpha into V equal to, now look at this, this is alpha and this is beta. So alpha plus beta into V equal to, by condition of vector space, alpha V plus minus alpha into V equal to 0. This means that this minus alpha into V must be equal to minus alpha V, otherwise it will be not satisfied, and hence the proof. Now fourth one, what is fourth? V not equal to 0 and then alpha V equal to 0. So we have to prove that here alpha, it is given alpha 0 equal to 0. Now if possible, suppose that alpha is not equal to 0, alpha not equal to 0, so alpha inverse exist. Alpha non-zero means alpha inverse exist, and again alpha inverse exist means apply the first condition. By first condition we write it as alpha equal to alpha inverse into 0, 0 equal to alpha inverse into 0 by first condition. Now for this 0, alpha into, for this 0 let us place alpha, alpha inverse into alpha v equal to, now look at this, apply the third condition of vector space, alpha times beta v equal to alpha beta v. So by that condition we can write alpha inverse into alpha into v, but alpha into alpha inverse 1, so we get 1 into v, 1 into v equal to v, fourth condition of vector space. We get here 0 into v, 0 equal to v, but in the assumption this is v, v is not equal to 0, which is contradiction. This is result and this is assumption, v not equal to 0. We get a contradiction due to this alpha not equal to 0, and therefore in if alpha v equal to 0 and v not equal to 0, then this alpha must be equal to 0. Now fifth one is a very obvious, we prove here fifth into alpha into v minus w equal to alpha into v plus, we write this as a minus w. Now apply first condition of vector space u plus v equal to, so I will get here alpha v plus alpha into minus w equal to, again this is here we replace this is minus 1, suppose alpha beta equal to, alpha beta equal alpha into beta, alpha in bracket beta v equal to fourth condition, so instead we write this as alpha v plus minus alpha into w, but by the third condition we can write this as alpha v minus alpha into w. So all the conditions of the theorems are satisfied, of the lemma are satisfied. Now we erase it. I hope you all of you get this idea how to prove this for 5 properties. This is a homomorphism definition. Now we prove one more lemma, again very big lemma. What is, if v is a vector space, v is a vector space over f, v is vector space over f, and if capital W is a subspace of V, then V by W is a vector space. It is a vector space over F, where for V1 plus W comma V2 plus W belongs to V by W. This is a set V by W, and alpha belongs to F. We define this how to add. V1 plus W plus V2 plus W equal to, how to add this, V1 plus V2 plus W, and second one is alpha into V1 plus W equal to alpha into V1 plus W. How to multiply this? This is the definition of addition and scalar multiplication in the set V by W. Then V by W is called as a quotient space. Now proof. We prove this theorem. Let us prove this. Let V be a vector space and W be a subspace. Then V by W is the set of all elements of the type V plus W, where V belongs to capital W. If we prove if V plus W equal to V dash plus W, then alpha times V plus W equal to alpha times V dash plus W. This is we want to prove. Therefore, now if first V plus W equal to V dash plus W, then we get that V minus V dash plus W equal to 0. Transfer to this side, left side, but this is nothing but V minus V dash belongs to W. Since W is a subspace, we write this as alpha times V minus V dash plus W, but this is equal to V alpha V minus alpha V dash plus W, or alpha V plus W plus alpha minus alpha V dash plus W. This is equal to this implies, and for this is nothing but alpha V plus W equal to alpha V dash plus W. Transferring to this one, we write this like this. For this, the same element is written in this form. Again, by definition of scalar multiplication, alpha into V plus W equal to alpha into V dash plus W. Now proved. This shows that scalar multiplication is well defined. Now we prove that this set is a vector space. Now to prove this, we have to show that first this is an abelian group. For this purpose, let us take V equal to, suppose V equal to V, suppose that V equal to A plus W, U equal to B plus W, and C W equal to small w equal to C plus W, where A, B, C are vectors. Now let us see the commutative property. Commutative property, V plus U plus W equal to, V means A plus W, and in bracket U means B plus W, plus W means C plus W. This is equal to A plus W plus, this is B plus C plus W. This is another element. This is equal to A plus B plus C plus W. But for this we can write, instead of this plus commutative property, associative property, we can take, we can write, these are the element, this is an element of vector space, and in vector space associative property is satisfied. So instead we add first these two elements, a plus b and plus w. This is equal to a plus b plus w plus c plus w, and this is nothing but a plus w plus b plus w plus c plus w, or this is v plus u plus w. Associative properties satisfied. Now let us prove the commutative property. Commutative property is again very obvious. U plus v equal to, what is u? B plus w plus, what is v? A plus w. This is nothing but b plus a plus w. This is equal to a plus b plus w, or this is same as a plus w plus b plus w, but this is equal to v plus u. Commutative property is satisfied. Now what is a 0 of this set? If we take 0 equal to 0 plus w, look at this, then v plus 0 equal to, v means a plus w plus 0 plus w, this is equal to a plus 0 plus w equal to a plus w, and therefore this 0 play a role of identity element. Now we write as v plus minus v equal to, what is v? A plus w plus minus a plus w. What is minus v? Minus v is minus a plus w. Then this is equal to a plus minus a plus w equal to 0, and therefore this element minus v, that is minus a plus w, is the inverse of a plus w. All the properties of abelian group are satisfied, and therefore this set v plus w, v by w is an abelian group. Now it remains to prove the properties of vector space. 4 properties of a vector space. What are that property? First property, alpha times u plus v. Alpha times u plus v. Here alpha into v plus u equal to alpha into, we have taken u as a plus w plus u means v plus w. This is equal to alpha times a plus b plus w. By definition of scalar multiplication, this is alpha a plus b plus w. This is equal to alpha a plus alpha b plus w, or this is equal to alpha a plus w plus alpha b plus w equal to alpha times a plus w plus alpha times b plus w, or this is equal to alpha v plus alpha u. First property of the vector space is satisfied. Now second property of the vector space, alpha plus beta into v equal to alpha plus beta into a plus w equal to alpha a plus beta a plus w, or this is same as alpha a plus w plus beta a plus w. This is same as alpha times a plus w equal to beta plus beta times a plus w, but this is equal to alpha v plus beta v. Second property of the vector space is satisfied. Now it remains to prove third and fourth property of a vector space. Third property of the vector space. What is third property? Alpha times beta v. Therefore, alpha times beta into v equal to alpha times beta into v means a plus w. This is equal to alpha into beta a plus w by definition of scalar multiplication. Again scalar multiplication, alpha into beta a plus w equal to, but these are this is an elements of vector space, and vector space this condition is satisfied, and in vector space by the definition of vector space this is alpha beta into a plus w, or this is same as alpha beta into a plus w, or this is nothing but alpha beta into v. Third property is satisfied, and fourth one is very obvious. This is equal to 1 into a plus w equal to 1 into a plus w, 1 into a equal to a plus w equal to v, 1 into v equal to v. All the conditions of vector space are satisfied, and hence the set v by w is a vector space. Today we have seen the definition of homomorphism, example of homomorphism, one theorem on a vector space, in which we have proved four properties of vector space, and we have shown that one important theorem of a quotient space, that is v by w, is a subspace of a vector space.